Okay, welcome back. Um, Week number 12, we will start lecture number 34. We were discussing reflection of the beam and chapter 9, and we discussed previously how to make an equation of elastic curve, and we did some couple of concept problems. So the deflection or deformation of the beam will also use to find the reaction for statically indeterminate beams. Okay, in this chapter we will see, in this lecture we will see this, and for this particular lecture we will follow the equation of elastic curve, means of elastic curve. Now let's see what are the statically indeterminate beams. Usually, for example, if you look at this figure, we have a cantilever beam, and the cantilever beam with a fixed end at A, and we have a pin joint at B, and we have a pin. So if we draw a free body diagram for this section, so we have AY reaction, moment at A, reaction at B, and we have AX as well. But AX will be 0, we take 0 over here. So we have only two equations, but three unknowns. MA, AY, and B. Now how to find these reaction? So with using the equation that for sum of forces is equal to 0 and sum of moment is equal to 0, we cannot find all three reactions, right? So in order to find, so we have to consider the deflection of the beam. Okay, now if you look at this, both ends are fixed. So if you look at this, so we have let's suppose there's a frictionless surface, it can move in this direction freely, so no reaction in horizontal direction. So sum of forces, if you draw free body diagram, so we have unknowns, four unknowns usually, because AX will become 0 uh, in this case as well. So four unknowns, but again we have two equations. So how to find the reaction in this case? So we have to consider deformation. For deformation, if you look at the above figure, this figure, so what we have? So if you look at A, the deflection is 0 as well as slope will be 0. And B, we have deflection will be 0. So using these boundary condition, we will get another equation, and with that equation and using the static equilibrium condition equation, we will find the reaction, all the reaction. Now if we look at this figure, the both end fixed. Now in this case, slope and deflection at A will be 0 as well as slope and deflection at B will also equal to 0. So at x is equal to 0, y theta will be 0 and y will be 0. And x is equal to L, theta will be 0 and y will be also equal to 0, because over there there is no movement in angular movement, so that's why theta will be 0, and same over here. And it's a fixed, so no vertical direction. So now with this we can find, we will get another equation and we will find what are the reaction, redundant reaction. And you can also think about how about this continuous beam. Suppose we have a beam, we have a pin support over here, another pin support over here, and we have this pin support over here. So what will be this case? So let's think about it, and you will find how to find the reaction. Okay, now let's see a concept problem. For this, determine the reaction at the support for the prismatic beam as shown in this figure. So we have a cantilever beam with a one end fixed and other end we have a pin joint. And we have now if we draw free body diagram, let's suppose if we draw free body diagram for this problem, and if I want to write sum of force in x direction should be equal to 0. So this leads me that Ax is equal to 0. Now sum of y forces is equal to 0. So this leads me Ay plus B minus WL is equal to 0. Now, and if you take, let's suppose moment at A is equal to 0. So this lead us to moment at A, this is reaction. So plus BL, this is, I'm writing the final form, and you can write with respect to sign and you will get the final form. And we have minus W L square by 2 for this one. L by 2 distance, WL is the force, and this will be equal to 0. Now we have 3 unknown, 2 equation. So what we have to do? So in this case we have to find we have to consider the deflection of the beam. Okay, so let's take a section. So let me change the color of my pointer. So let's take a section between A and B. Let's take a section. Since it's a continuous load, so there will be the moment equation will be continuous, and let's take this distance as x. So I am taking the section, let's suppose at C between A and B, and let me draw a free body diagram for that section. So we have A, AY, we have a moment at A, we have a distributed load, and we have a shear force V acting over here internal, and we have bending moment M over here. And there will be a distributed load, and this distance let me take as x. And this distributed load I can take as a concentrated load, and that concentrated load will be simply W into x, and this distance will become simply x by L. Sorry, x by 2. Okay, since we are interested in the equation of moment, so let me take this point. This is my C point. So moment about C will be equal to 0. So I can write M plus W x square by 2 plus MA minus AYL x is equal to 0. So this is my equation of moment, and if I want to write m will be ayx minus w x square by 2 minus ma, and this equation will be valid from a to b for whole length of p. Okay, that is equation. Now let's find the equation of elastic curve. So if I want to write equation of elastic, for the equation of elastic curve, I know that okay, ei dy by dx, and that will be equal to mx. And if I want to write ei dy by dx, so that will be ay x minus wx square by 2 minus ma. Now this is my equation, and I will use this equation to find the value uh, of I will use this equation of elastic curve, and then I will find the reaction. Okay, sorry, let me put over here, this is my equation number 1 and this is my equation number 2, and we will use this later. So if I integrate it, so ei, so I can write ei theta or ei dy by dx, and that will be equal to what? If I integrate it, so that will become a y x square by 2 minus w x cube by 6 minus m a x plus c1. Now if I again integrate it, so first I'm integrating with x, so I'm integrating with x. Okay, now let me again integrate this with x. So this is my equation, let me put capital A, and again integrating with x. So this will become ei y. Now this equation will become ay x cube by 6 minus w x4 by 24 minus m a x square by 2 plus c1x plus c2 is equal to c2, and this will be my equation number p. Okay, now what boundary condition will have? At x is equal to 0, we have theta is equal to 0. So if we put this value, so if then equation A will become C1 will be equal to 0, and for x is equal to 0, that is at A, at point A, so y A will also equal to 0. So let me write subscript. So this leads us to C2 is equal to 0. So the above equation, we have equation A will become EI theta ax square by 2 minus wx cubed by 6 minus ma x, and equation B we have ei y, and this will become ax cubed by 3 minus wx4 by 24 minus ma x square by 2, and because c1 and c2 both are 0. Now what else we have? So if we put, so let me change the color of my pen. If you put in previous equation, if you put let me write all three equations in this page as well, so that we find, so ay, that is from sum of forces is equal to 0, plus b minus wl is equal to 0. So we give this equation 1. So we have another equation with respect to moment. So that was m a minus bl, plus bl minus wl squared by 2, and this is equal to 0. This equation number 2, and we have the equation for theta and y with a constant. So theta we don't need, but the equation of elastic curve for this problem was ey ay x cubed by 6 plus, minus wx4 by 24, and we have minus ma x squared by 2. Now what we have? We have at x is equal to L, that is at B, the deflection is also equal to 0. So this equation, let me write, this is my equation number 3. So this equation number 3 will lead me to 0 is equal to ay L cubed by 6 minus wl4 by 24 minus ma L4 by 2. Now if you look at that equation 1, 2 and 4, we have 3 equations and we have 3 unknown. So by solving equation 1, 2 and 4 simultaneously, what we have? We have ax will be 0, then if we calculate, so ay, that we have 5 by 8 times wl, ma will be 1 by 8 times wl square, and we have b, that is equal to 3 by 8 times wl. Now by considering the deflection, we can solve statically indeterminate problem as well for the beam. We have seen this concept application. 9.5. Okay. Okay, let's see sample problem 9.1. Uh, for the portion of AB of the overhanging beam, derive the equation of the elastic curve. So we have only considered this section AB and we have to find the equation of elastic curve for that one. Determine the maximum deflection. And we have to find the maximum deflection, and then we have to find the value of that maximum deflection by putting this value. Cross section is given, that is W14 by 68, and the section properties is also from the NAGSC. I will be 723 inch 4, P load is given 50 kilopound, and the length of the beam is 15 feet L, and this A is 4 feet, so total length is 19 feet. First, what we will do, first we will develop an expression of mx, drive differential equation for elastic curve, and obviously we need reaction for that A and B. And then we integrate differential equation twice by applying boundary condition to obtain the equation of elastic curve. And locate 0.0 slope, a point of maximum deflection, because when it bends, the maximum deflection will occur where we have slope 0. And we put the value of cross section and E, then we will get the maximum deflection in numerical terms. Okay. So first develop an expression of mx. So first, obviously, we have to find what are the reaction, draw a free body diagram, and if we draw, and the reaction will be RA will be PAL by L, and it will be acting downward, and RB will be acting upward, and it will be equal to P multiply 1 plus A by L. That you can find easily using the static equilibrium condition. Okay, now if you take a section, so taking a section between A and B, somewhere section between A and B, D, and just draw free body diagram for that one. And we are interested in moment equation. So M will be simply what? M, if I want to write the equation, so M will be what? M plus P A by L times X is equal to 0, and the M equation, the moment equation will be like this, and it is valid from for A to B, and we are also interested for A to B, and this is valid from section A to B. So differential equation for elastic curve, so with that value we already know that is EI d2y by dx square is equal to equation of moment in terms of x. So we put the value, so this is differential equation of elastic curve. Now we integrate it using the differential equation with respect to x, and this first we integrate, we get this value, and again we integrate, so we get C1 and C2. These are two constants, and how to find these constants? We have boundary condition. The boundary condition is x is equal to a, y is equal to 0, and x is equal to l, y is equal to 0, since this equation is valid for section A, B. Okay, so when we put boundary condition, so we have equation of C1 and C2 are these equations. So dy by dx is equal to minus 1 by 2 pa by l x square plus 1 by 6 pal. By putting the value of C1 and C2, so when we put x is equal to 0, so if you put x is equal to 0 in this equation, so y will be 0, so this C2 will become 0. So when we put x is equal to L in this equation, so C2 is already 0, so C1 value we will get 1 by 6 PAL. So, and when x is equal to 0, that is A, point A, and x is equal to L at point B. So, by substituting the value of C1, so we have this equation, and we simplify it slope equation like this. And value of putting C1 in equation of elastic curve, so we have equation of elastic curve y is equal to PAL square divided by 6EI multiplied by x by L minus x cube by L cube. Now, if you look at this bending of the beam, so it will bend something like this. So at B the deflection is 0, and at A the deflection will be 0. And we are interested what will be the maximum deflection between A and B. And we drive the equation of elastic curve for this portion. Now if you look at this, maximum deflection occur where the slope will be 0, means if the slope will be horizontal straight line. So means if you make a horizontal straight line, so that's mean that the slope will be equal to 0 at that location. Now on that location, so we have to find where is this location. Let me put x. Let put xm. So it will be 0 where the slope will be 0, means where this value will be 0. So if you put dy by dx is equal to 0, and we simplify it using this equation, so 6 times ei will become 0, PAL, that will also be 0, so you only left with 1 minus 3 times x by L square, and xm will be simply L by under root 3, or xm will be 0.0577 times L. At this location, deflection will be maximum. Now, putting this in the equation of elastic curve over here, so y max, putting x is equal to 0.577 times L. So by putting this equation, so y max in terms of equation 0.0642 PAL square by 6 EI, putting the value of A, L, E, I and P. So P is 50 kilopound, A was 48 inch, so it was given 4 feet, so 40 in terms of inches, because E is also in inch. So, and 15 feet we converted into inches, that will become 180 inch, divided by 6 times E, Young modulus, and I, section modulus. And we calculate Y max as 0.238 inch. So if you look at the deflection, the overall length of the beam is 19 inch. And that is 90 in terms of 19 feet, sorry, and in terms of it is 228 inches, and the deflection is 0.238 inch. So it's a very small deflection. So now you can find the maximum deflection where the slope will be 0 for overhanging beam or for the simply supported beam. Now in this problem we didn't consider this section as it was not mentioned to find the deflection. So maximum deflection can be at C as if we consider the whole beam, the maximum deflection can be at the C location or point. So we have to consider this part as well if we want to find the maximum deflection for the whole beam. Okay. Now this was sample problem 9.1. So I will suggest these are the problem. Some of the problem related to the simply statically determinate beams, and other problem are related to statically indeterminate problem. So try to solve it. and you have to make the equation of elastic curve using the first. You will take differential equation of elastic curve, and then you will find the equation of elastic curve now using the boundary condition, and try to solve these problem uh, as assignment. Okay, and the reading assignment is just look at this sample problem 9.2. Okay, and that sample problem is again simply supported beam with a distributed load, and also check the sample problem number also 9.3. Okay, that 9.3 is us for the statically indeterminate. Okay, we will solve a couple of other exam problem as well. Uh, Next lecture we will see method of superposition, and then we will solve some other problems as well. So thank you very much.